This is a lesson on double slit interference in the light and optics unit where I'm looking at interference of light. In a prior lesson, I had talked about Huygens principle and diffraction, and also I've looked at single slit diffraction and how to locate dark places for a single slit diffraction pattern with all that interference. So the double slit experiment is a very famous experiment. It's often referred to as Young's double slit experiment. And it was used as the definitive proof for the wave characteristics of light. And I will say on prior lessons, if you just take diffraction happens for all waves and you see it happening for light, then light must act like a wave. This is definitive proof of the wave characteristic of light, and I will also put on here and particles. We will be looking at the wave-particle duality and why the double slit experiment shows that particles are waves. Okay, the setup here is we're going to send a beam of light through two very narrow slits, and you can see that here, separated by a distance d. They're separated by a distance d here. We're going to project the light onto some sort of screen and look at the interference pattern. And if light wasn't a wave, we would not see this pattern. We would just see like one single, like if you threw basketballs through a door, right? They don't diffract after they go through the door. They just follow the straight line. But that's not what we're seeing. We're seeing diffraction is happening with light. It's extending into those regions past the barrier. So how do we look at this? There's the diffraction pattern for real. This is a real laser that went through two slits, and you can see that the pattern is different than the single slit. They're very narrow. The fringes in here are very, very narrow, and they're also very uniform. The brightness here is very uniform across the center, and so that's what we're seeing with the double slit interference pattern. I wanted to contrast it with the single slit diffraction pattern. The single slit diffraction pattern is on the bottom. And I like this picture. I grabbed it off the internet because it has the shape of the slits over here. So you can see this is a single, pretty wide slit. And this is the diffraction pattern that we get from it. We have a very wide central fringe, and then the outside ones get dimmer as you go out. Two narrow slits is right here, and you can see for two narrow slits, their fringes are much narrower, very, very small compared to the single slit. So there's many more of them across here. I included this one up here because this is the combination effect. If I take a wide slit, if I take two wide slits, what I'm going to get is the interference pattern of a double slit overlapping with the diffraction pattern of a single slit. And you can see that this top pattern here is the combination of the bottom pattern and the middle pattern. They combine together. And that is not by magic. We can see this mathematically as well with intensity. And it turns out when you're adding these waves, you're multiplying them. So if there's some place where there's 0 here, you can see that it goes to a dark spot here, and it lines up with a bright spot. When I multiply 0 times anything, I get nothing again. And so you can see that it's pretty dark in that spot where I might expect there to be a bright spot. And that's apparent over in the intensity pattern here. Here's this blue one you can see over here is the one slit diffraction. That's the blue pattern. And it's pretty wide. It goes out to 30 degrees. We saw that it's a pretty wide angle. We saw that it's a pretty wide angle in the diffraction of single slits in the prior lesson. With two slit interference, these are much smaller angles. You can see that it's going to be 5 degrees, 15 degrees in here. They're not going to be very large angles for the interference pattern for a double slit. And we can see that here. These are not separated by large angles. Only the single slit. The double slit isn't. And so when we add those two patterns together, we actually multiply them. And you can see that where there is supposed to be a peak for the two slit, the single slit went to 0, and overall the actual pattern, the two of them together, has 0 there. So that's corresponding to like this point here where there should be a bright spot, but we're not seeing anything. So that's the difference between the double slit pattern and the single slit pattern. Let's look at how to locate angles for the double slit. The double slit we can look at very similarly to what we did for single slit diffraction. What we're going to do is we're going to look at two waves, one from the first slit and one from the second slit. And all along the screen here, we can see that they're going to interfere at maximum values or minimum values all along that screen. And we're going to derive the path length difference very similarly to single slit. What we do is we look at those two waves, we look at their path length difference, and what it comes down to is the path length difference can be represented by this side of this right angle formed by their two rays. This distance is so far, L1 and L2 are so large that we can assume that these two are essentially parallel to one another, and this path length difference between these two, and you can see it a little bit better in this picture here. Here's slit 1, here's slit 2, and there's the path length difference. This is a right angle, and we can relate the path length difference to the slit distance and the angle from that central axis. So there's the path length difference, d sine theta. If I want constructive interference, I set it equal to m lambda, right? That's true for any wave. We set the path length difference equal to m lambda for constructive interference, or a half integer of lambda for destructive interference. And that's how we would find the bright spots or the dark spots for this interference. And it's okay to find the bright spots, the constructive interference for two slits, because these are approximately evenly spaced. And so we're looking at the bright spots, you can locate them, as well as the dark spots. You'd be able to locate the difference. And so those are pretty consistent. These are very small distances and pretty small angles. One thing I'll also throw in here as I'm talking about small angles is it may be true, but you will need to do a test. It may be true for small angle, for very small angles, very small angle, very small theta. If it's very, very, very small, I would say less than 10 or 15 degrees. Usually I'll say like 10 degrees. Some people say 15 degrees. If this angle's less than 10 degrees, what we know at that situation is sine theta. If you plug it into the calculator, sine theta is approximately equal to theta in radians at that value of theta. And you can plug it into your calculator, but theta needs to be in radians, not in degrees. And so that's true. This is what we call the small angle approximation. This is not always true for all problems. So I'm bringing it up as something that you can use, the small angle approximation, if you know those angles are going to be small. If you don't know the angles are going to be small, or if you know that they are large angles, you cannot use this. Another part of this identity with small angle approximation is tan theta is approximately equal to theta in radians as well. So very useful approximation if it applies. Make sure you check that you have a small angle, less than 10 degrees or so. Don't use it for anything larger than that. So the example problem I picked for the two-slit interference addresses this sort of missing fringe problem. The equation isn't too hard to use, so I'm not going to do more of a straightforward application. I wanted to look at this missing fringe problem. And I pulled this picture off. You can see that this is off the internet, and I liked it because it was very apparent here that there was a lot of fringes. These are all the two-slit fringes here, and they're being enveloped by the single slit, right? The single slit pattern here. And where there should be a bright fringe for the double slit, it gets canceled out by the dark fringe of the single slit. And so that's the idea of the missing fringe problem, is where we expect there to be some sort of fringe, there's not. And it's this overlapping of this double slit bright spot with the single slit dark spot. So let's look at this a little bit more particularly. What I'm going to do is delete this and actually look at the problem here that I selected for us. So let's get rid of this. And it says monochromatic light, so single wavelength light, is directed at two slits. Each slit is 6.5 micrometers wide, and the slits are separated by 39 micrometers. So there's two slits. The distance between them, they're telling me D equals 39 micrometers. And when I look at the width of them, the width in here of them, W, equals 6.5 micrometers. So we have the size of the slits and we have how far apart they are. Which double slit bright fringe does the first order dark fringe fall upon? So that's what we're looking at here. We're looking at, we have a bright fringe lining up with a dark fringe, and we have a missing fringe. So what we're going to do in this situation, I'll put this over here for part A, we're going to note that that happens at the same angle, the same theta. On a screen, they actually line up with one another. So we know that the angle in the one is going to be equal to the angle in the other. And so what I'm going to do is use these two equations for the single slit and the double slit. This is the 2 slit and this is the 1 slit. And I'm going to set sine theta equal in both of them. And I'm going to distinguish their two m values separately. The m value for the double slit I'm going to call m2, and the m value for the single slit I'm going to call m1. So when I set sine theta equal to sine theta, m2 lambda over d equals m1 lambda over w. Right? There's a d in this equation, and that corresponds to m2. There's a w in this equation, and that corresponds to m1. Well, it says first order dark fringe. So the first order dark fringe is going to happen at m1 equals 1. And we want to know which double slit bright fringe does the first one fall on. So we want to solve for m2. This isn't too bad of an equation. The lambda cancels on both sides. I don't even have to calculate the angle. I can just say m2 equals m1, which is 1, d over w. I'm given D, 39 micrometers, over the W, 6.5 micrometers. And when I divide those two, I will see that M2, the order number of the 2 slit interference, is going to be 6. So, and I expect an integer value. If they're lining up exactly, it will be an integer value. So the first order, this first order single slit diffraction pattern dark, is lining up on the 6th double slit interference pattern bright. That's a lot to keep track of, but that's what's going on here. So that's our answer for part A. Part B says if the screen is 50 centimeters away, how wide is the central bright fringe of the single slit diffraction pattern? So they want to know this width here. What is the width of this central bright fringe for the single slit diffraction pattern? What is the width here? So that's why I included this picture over here with the L and the Y. We know the distance between the slits and the screen, the L value, is going to be 50 centimeters. And so when I look at this right triangle here, 50 centimeters along here, here's Y, I can set up this relationship that tan theta equals Y over L. So that's what I'm going to do. What they're asking me for, however, is how wide is the central bright fringe. So what I'm going to note for the central bright fringe, here's the central axis. I'm going to have to double that Y value in order to get the width of that central bright fringe. So actually I'm going to solve for a 2Y. 2Y is going to equal 2L tan theta. So now I'm ready to solve. If I had theta, I would be able to find that width. To find theta, I have to find the dark spot of a single slit diffraction pattern, and it's the first dark spot. So I'll go sine theta equals 1 lambda over W. So then when I solve for theta, I get the inverse sine of the wavelength, which is 550 times 10 to the negative 9th. And I'll divide that by the width. They tell me the width is 6.5 micrometers. So I'll put in 10 to the negative 6th in there. So this angle that I get is actually pretty small, 4.854 degrees. Okay. So that's the angle we're at. I'm going to take that and put it into my width equation here. I'm going to have to find the width of that central bright fringe. I'm going to take 2 times the L, the distance between the slits in the screen, which is 50, and then multiply it by tan of the 4.854 degrees. And when you multiply this through, run it through your calculator, you get that width to be 8.492 centimeters is what you get. I left 50 in centimeters, so that's what I get out as centimeters. So at 50 centimeters, I see that central bright fringe is going to be about 8 centimeters. So that's pretty wide for central bright fringe. It is what it is. And you can see the angle here. It's about 5 degrees. That's not bad. So that's the answer to B. C says, what is the distance between the bright fringes on the double slit pattern? So they want the distance between these fringes on the double slit pattern. So let me get rid of some of this stuff here that I've already written out. We don't need some of this in here, and I'll keep the equations. Okay, so to find the distance between bright fringes. So let's go from the central bright fringe for the two slit to the next one where I know m equals 1. So this is the m equals 1 bright fringe, and this is the m equals 0 bright fringe for the two slit. The two slit equation is d sine theta equals m lambda. I know if I want to find the y value, I will go from the central bright fringe m equals 0 to m equals 1. So that's the m that'll go in here. I'll find theta 1 for the two slits. So theta 1 is the inverse sine of 1 times the wavelength, 550 times 10 to the negative 9th, and divide by the distance between the slits. This is the distance between the slits, which is 39 micrometers. 39 times 10 to the negative 6. So theta 1, I'm getting in here to be a pretty small angle, 0.8080 some stuff. So that's a very small angle, right? And that's what I suggested that you expect, that these angles between the double slit fringes are going to be very small. So let's take that angle. I want to find y here. So I know that y is L times tan theta. We figured that out on the previous problem. And so I'm going to take that 50 centimeters and multiply by tan of my tiny angle here. And when I run that through the calculator, that distance between the central bright fringe and the next bright fringe for the two slit is going to be less than a centimeter, 0.705 centimeters. So pretty tiny on there, very tiny. And so that's consistent with what we observed. The single slit has a wide central bright fringe, and the double slit has a lot of teeny tiny brighter ones that are less distance apart.